This episode is brought to you by my friends at Patreon. And, once again, by Singularity G3, my Twitter friend who makes all the art possible. For those just joining us, this is the second part of the next level of a series of videos demarcating our position in the universe. For a crash course on the map I'm using, the route I'm following, and the various objects observed, please see the previous video. Off the bat, let me be very clear. I'm flying blind on this one. Unlike the previous map, which was more or less self-explanatory, this map denotes far more esoteric concepts than just, it's a star, and it's orange. The overlapping objects make the labels hard to discern, and I am likely to make a mistake as I go. That said, we left off at the queen of star clusters, the Pleiades, which forms the gateway to the Taurus dark cloud, which is either part of or synonymous with, I still don't know which, the Taurus molecular cloud. The Taurus molecular cloud is the closest star-forming region to Earth, and part of the Radcliffe Wave, the gigantic river of star-forming regions that comprises much of our local Orion arm. The stars within the Taurus cloud are all young, less than 2 million years, and still in the process of collapsing into stars. In fact, the type specimen for protostars, T Tauri, is located in this region. T Tauri stars have yet to implode the material in their cores, and, rather than nuclear fusion, shine via the heat of their own collapse. Like black holes, not only are they surrounded by accretion disks, but these disks generate vast magnetic fields which flare off in gigantic jets erupting from their star's poles. T Tauri is actually a triple star system comprising a binary of protostars orbiting each other at a distance of about 7 AU. Or between Jupiter and Saturn in our system, orbited in turn by a third protostar roughly every 1,000 years. The distant orbiter, T Tauri North, is about twice the mass of the Sun, as is the larger of the binary. Despite being the namesake for its type, T Tauri North is actually very atypical for a T Tauri star, as it is far younger than average, at less than 1 million years old. Its jets create shock fronts as they slam into the interstellar medium, known, with typical astronomical passion, as Herbig-Haro objects. Some of the best images we have of circumstellar disks have been taken of stars in the Taurus cloud stellar group, the Taurus Auriga Association. H.L. Tauri, whose glorious disk has illumined many of my previous videos, albeit often cast in different roles, is in fact a very young, as in less than 100,000 years, T Tauri star, while its disk is about 1/10 the mass of the Sun. When ALMA imaged that disk in 2014, it threw the astronomical community for a loop. To see such an advanced disk, with gaps already presumably cleared by unseen protoplanets, around a star so young, showed that planetary formation was a much faster process than previously envisioned. AB Aurigae, side note, would you prefer a different pronunciation, is an older protostar of about 4 million years, whose circumstellar disk is woven into beautiful spiral arms, likely caused by its material fragmenting into clumps, gradually coalescing into planets. A kink in one of those arms suggests it may be hiding a planet of about 4 Jupiter masses, orbiting its star at about twice Neptune's distance. Another planet, or possibly brown dwarf, may explain a gap observed at 100 AU. In 2018, I named Ci Tauri, a star in the Taurus Auriga Association, one of the discoveries of the year. The reason was that the star, a T Tauri star barely 3 million years of age, appeared, thanks to radial velocity measurements, to possess 4 super-Jupiter-sized planets in its retinue, even though such monsters are estimated to take 10 million years to form. Since then, the picture has become more clouded, with many declaring the purported planet, Ci Tauri b, an artifact of the star's 9-day rotation, while the other planets as yet remain unconfirmed. One, identified this year and christened Ci Tauri c, is a 3-Jupiter-mass planet supposedly orbiting its star in 25 days, and apparently a solid enough hit for the NASA Exoplanets Archive to declare it real, which would still be unfortunate for our hypotheses of planet formation. West and 35 parsecs north of the Pleiades, we arrive at Melot 20, better known as the Alpha Persei cluster, which comprises not only the above star but also several of the brightest stars in the Perseus constellation, including Delta and Epsilon Persei. Though not the best-known star in said constellation, Beta Persei, otherwise known as Algol, or, for that matter, Omicron Persei. The cluster totals about 500 stars, most of which are bright, blue B-types, spread over about 11 light-years, all between 50 and 70 million years old. The brightest star in the cluster, Alpha Persei, stands out from the crowd. Also known as Mirfak, which means elbow, Alpha Persei is an F-type supergiant star, similar to Procyon, except 6 times more massive and 5,000 times more luminous. It is moving off the main sequence, and is already bloated to 50 times the radius of the Sun. Although it lies in a similar position on the HR diagram to Cepheid variables, the great pulsing monsters used to calculate stellar and galactic distances, it is not one itself. Radial velocity, never a reliable method when dealing with aging stars, has purportedly detected a planet of over 6 Jupiter masses orbiting it every 128 days. Given that such an orbit would be unstable over even a short time period, this is considered doubtful. Passing by 2 recently discovered open clusters of no current repute, we arrive at NGC 1333, a reflection nebula venerable enough for the New General Catalogue. Discovered in 1855 by German astronomer Eduard Schonfeld, whose life story appears to have largely comprised pretending he wasn't into astronomy for as long as his father paid attention. It was 19th century Germany, what you gonna do? The nebula comprises the western end of the larger Perseus molecular cloud, and is also home to the dark nebulae Barnard 1 and Barnard 2. It comprises about 100 stars, all less than 1 million years old, and in the T Tauri stage, many blasting their jets into the interstellar medium. Fascinatingly, in 2023, the Spitzer Infrared Telescope found the nebula to contain over 50 brown dwarfs, 15 of which may be below the 13 Jupiter mass threshold to fuse deuterium, making them so-called sub-brown dwarfs, though some prefer to call them planetary mass objects. 5 of them present an infrared excess, suggesting they may be surrounded by their own protoplanetary disks. Brown dwarfs are easier to see in young clusters, as they have yet to cool down and still shine brightly in the infrared. Rimward and 6 parsecs north, we arrive at IC 348. IC, or Index Catalog, is the name for later additions to the New General Catalog. IC 348 is another cluster of about 4 young stars, centered on a B-type binary. Like 1333, 348 is home to several brown dwarfs, many of whom possess circumstellar disks. In 2023, James Webb confirmed them as the least massive brown dwarfs on record, at just 12 Jupiter masses. If these objects had been found orbiting another star, they would have been called planets. How a free-floating stellar object of such tiny mass can form is still uncertain. Did it form as stars do, from gravitational self-collapse, or as a planet, before being ejected from its stellar cradle? IC 348 is one of the locations outside our solar system in which amino acids, the building blocks of proteins, have been identified, showing that the ingredients for life as we know it are present across the universe. Passing over another recently identified cluster, we enter the California Nebula, which, rather surprisingly for a nebula, does actually resemble its namesake. Discovered in 1884 by one of my heroes, E. Barnard, its latitude, surprisingly, maps onto central California. Like all H2 regions so far, the California Nebula owes its luminescence to a gigantic star, in this case, Chi Persei, an O-type monstrosity 30 times as massive and 250,000 more times as luminous as the Sun. It is considered part of the Perseus OB2 association, though its striking distance from that group suggests it may have been knocked off course by a supernova. The next object of note in this journey is Stock 10, a loose cluster of about 20 stars discovered by German astronomer Jürgen Stock about 60 years ago. Next to that, we find the Flaming Star Nebula, an emission nebula surrounded by the variable star A.E. Aurigae, an O-type star 60,000 times as luminous as the Sun. A.E. Aurigae is not the source of the nebula, but instead is plowing through it at high speed, creating a wake of interstellar cloud. Like Chi Persei, it is considered a runaway star, possibly due to a collision in the Orion Nebula. Some astronomers speculate that the collision may have been with the binary star Iota Orionis some 2 million years ago. And now we pass into one of the major features of our local galactic geography, the Orion Aridus superbubble, which is on this map even though our own superbubble, the local bubble, is not. I assume because ours isn't an H2 region. For those who missed my previous video, an H2 region, spelled like this, and marked on the map as a red sphere, is a region of doubly ionized hydrogen, usually created by the raging power of a giant star, or in the case of Orion Aridus, multiple stars. Orion Aridus surrounds and is believed to be caused by the stars of the Orion OB1 association, a group of several gigantic O and B-type stars, most notably the stars in Orion's belt and sword. They are tied to the Orion Molecular Cloud Complex, two colliding space clouds whose collapsing gas creates a region of active star formation, including the famed Orion Nebula, with its stars all less than 12 million years old, the most active being the Orion Nebula cluster, which actually extends above the Orion Nebula and forms the middle of Orion's sword. Comprising 2,000 stars spread over about 6 parsecs, the Orion Nebula cluster is the closest region to Earth where such giant stars are formed. While Orion has been subject to mythic interpretation the world over, I already covered it in my video on Betelgeuse, see above, and so will not do so here. Our first stop in the bubble is the recently discovered cluster UPK 385, about which I can learn little save its age of 12 million years, which suggests it is part of the Orion OB1 association. Rimward of that, and 53 parsecs south, we arrive at the loose open cluster NGC 1662, about which I can learn nothing at all. Heading east, we pass into a barely discernible pile of H2 regions, two on top of each other, separated by 25 parsecs, both obscured by the larger Orion Aridus superbubble. The top region is that produced by the star HD 34989, a B-type star about 12 times the mass and 1,500 times the luminosity of the Sun. The lower, known as the Angelfish Nebula or the Lambda Orionis ring, is believed to be the remnant of a past supernova, currently illuminated by the searing power generated by the OB binary star Meissa, also known as Lambda Orionis, the star which forms Orion's head. Meissa, appropriately, means the shining one, though it was actually a misattribution and originally referred to Gamma Geminorum, which, ironically, is less than 1,000th as luminous. Meissa proper, the larger of the two stars, is gigantic, 12 times the Sun's radius, 27 times its mass, and 165,000 times as luminous. Its stellar wind is believed to reach 2,000 kilometers per second, 150 at the speed of light, and cause it to lose mass equivalent to Jupiter's moon Europa every year. Its larger radius than a typical O-type suggests it is moving off the main sequence, and, at less than 2 million years old, is already entering the final stages of its life. Its companion, Meissa b, is a B-type star, only 6,500 times as luminous as the Sun, and about a third as massive as its primary. The system is orbited by an F-type star, which in turn may be orbited by a lesser companion, likely a brown dwarf. The system forms the core of the Lambda Orionis cluster, also known as Colander 69, a small cluster with a number of small stars and brown dwarfs, including many with suspected circumstellar disks. Moving past two recently discovered clusters, we arrive at UBC 17b and Gulliver 6. No, I couldn't determine who initially bore that name. Turns out it's hard to Google. Neither of these clusters is notable in and of itself. However, they are only separated by 1 parsec, and some have speculated that they may form a gravitationally bound binary. Studies suggest up to 12% of clusters in our galaxy could exist in binary or higher groups, though very few have been confirmed to date, a fact sure to change with more Gaia data. 10 parsecs north of that, we arrive at the Sigma Orionis cluster, an open cluster dominated by the star Sigma Orionis, which appears as a dim companion to Alnitak, the lowest star of Orion's belt, and stands across from the famed Horsehead Nebula, whose form its light illumines. Sigma Orionis is itself not a single star, but a tight triplet comprising 2 O-type stars orbiting each other every 143 days, orbited in turn by a B-type every 157 years. All three are between 10 and 20 times the mass of the Sun, but while the outer two are 16 and 19,000 times as luminous as the Sun respectively, the primary, known as AA, is 41,000 times as luminous. They are all of different ages, with the oldest estimated to be 1.9 million years old, and the youngest just 300,000 years old, suggesting that despite their proximity, they did not form together. The system also includes 3 other stars, making Sigma Orionis that astronomical rarity, a 6-star system. The faintest of the outer stars, C, orbits the trinary at about 100 times Pluto's distance. Its mass, at 2.7 suns, would likely make it a low-end B-type. C has a companion, likely a brown dwarf, though little is known about it at present. D orbits at around 20 times Pluto's distance and is a very typical B-type of 7 solar masses. The star, if you will, of the Sigma Orionis system, at least from an astronomical perspective, is E, a peculiar variable star with an overabundance of helium and a strong magnetic field, which orbits the primary at around 400 times Pluto's distance. Said magnetic field is likely responsible for E's brightness varying over its 1.9-day rotation, and may also be the reason for its helium abundance, despite its young age, as it could strip hydrogen from the surface and send it toward the poles, leaving heavier helium exposed at the equator. E has a companion of its own, possibly a red or orange dwarf star. The wider cluster comprises over 40 stars, mostly A or B type, with a few dim M types and brown dwarfs. There are also a number of planetary mass objects, most notably S Orionis 70, the first free-floating planet, or planetary mass object, ever found. At just 3 Jupiter masses, it forced the IAU to define an extrasolar planet a full 3 years before the Pluto debacle. In a somewhat peeved missive, they proclaimed that any such objects were, quote, not planets, but sub-brown dwarfs, or whatever name is most appropriate. Despite that name being about as imaginative as a tofu sandwich, it appears to have stuck. So if anyone asks, is there such a thing as a rogue planet? You can say, no there isn't, by official decree. 9 parsecs south, we arrive at SH2-279, otherwise known as NGC 1977, or the Running Man Nebula. SH2-279 is the H2 region generated by 42 Orionis, a B-type star about 12 times the mass of the Sun. Its reflection nebula magnifies and blurs the light from the star, shaping it into the hilt of Orion's sword. 42 Orionis' intense ultraviolet radiation blasts the surrounding protoplanetary disks, causing their material to evaporate, while its stellar wind blows it into comet-like tails. Their raging T Tauri stars are in turn blasting their jets into 42 Orionis' stellosphere. I must confess I am a little confused here. The map lists NGC 1977 as an open cluster, yet every source I can locate simply describes it as an alternate name for the Running Man Nebula. I can only assume that the cluster was meant to be NGC 1981, a cluster in line with 42 Orionis that rises above it like sparks from a fire, and named on the map as UBC 207. Of course, I'm probably wrong. Next to it, and 3 parsecs south, we find NGC 1980, sometimes called the Lost Jewel of Orion. It is an open cluster and nebula dominated by the tight ONB binary Iota Orionis, also known as Hathisa. Its nebula scatters the light from the giant stars, forming the tip of Orion's sword. Hathisa, I'm afraid, is not an ancient name, but another bit of officially ennobled meaningless verbiage from Antonin Betsevar's 1951 Sky Atlas. Why we haven't kept its Arabic name, Nayir al-Saif, the bright one of the sword, I have no idea. The 2 stars of Iota Orionis, an O-type 69,000 times as luminous as the Sun, and a B-type 9,000 times as luminous, orbit each other in just 29 days, at a distance closer than that separating the Sun from Venus. Despite this, the 2 are believed to be of separate ages, which, combined with the high eccentricity of their orbits, suggests the smaller star was captured by the larger. 2 other stars, a B-type and an A-type, orbit the binary at distances of 5,000 and 40,000 AU respectively. NGC 1980, the cluster over which Iota Orionis holds court, may only be loosely tied to it, likely due to a rogue star barging through and knocking it off course. Some have even argued that it is not tied to Iota Orionis at all, and may be separated by as much as 40 parsecs. It is home to at least 148 stars, all of which are young, less than 1.8 million years old, and some of which are Tauri stars. And now we arrive at one of the prized destinations of this trip. Astronomers past called the Orion Nebula the Great Nebula of Orion, and it's not hard to see why. Even through a small telescope, it reveals itself as a radiant, ghostly cloud, easily outshining the other components of the sword. Although visible to the naked eye, it played little role in the mythic visions of humanity until the invention of the telescope. While the brightest stars within the nebula have been known since antiquity, the nebula itself apparently escaped notice, to the point that some have even speculated that it only recently brightened in our skies. This is entirely possible. Indeed, we know for certain that it was not visible 50,000 years ago, as the stars within had not yet blasted away the gas that had obscured them. There are no myths unambiguously tied to the Orion Nebula. Ptolemy's star charts don't record it, and even Abd al-Rahman al-Sufi, the Persian astronomer whose Book of Fixed Stars records the first image of the Andromeda Galaxy, failed to note it. Johann Bayer, the German astronomer who, in his 1603 Atlas of Tycho Brahe's star observations, invented the practice of naming a star by a Greek letter in order of brightness, followed by a Latin genitive denoting the constellation, the so-called Bayer designation still used today, also failed to observe the nebula, but nonetheless identified a star at the nebula's location, which he named Theta Orionis. The Orion Nebula only appears in the historical record in 1611, when it was first recorded, not, surprisingly, by Galileo, but by French astronomer and antiquarian Nicolas Claude Pierresque, who claimed he was, quote, surprised to see a, quote, small illuminated cloud. This discovery was not widely circulated at the time, leading many to grant discovery to Galileo's intellectual heir, Christian Huygens, in 1659. Galileo did, however, discover that Theta 1 Orionis, the stellar engine that illuminated the nebula, was in fact a tight group of 4 stars, now known as the Trapezium cluster, making an accurate sketch of it in 1617, though his finding was not published in his lifetime. In 1769, Charles Messier placed the Orion Nebula in his catalogue of annoying comet-like objects, granting it the number 42. He also noted that it contained 11 stars, including 4, quote, strongly compressed to each other and of extraordinary brilliance. In 1810, William Herschel, cementing his status as a potential time traveler, described the Orion Nebula as, quote, an unformed fiery mist, the chaotic material of future suns, and speculated that, as his observations of the nebula differed from those described by Christian Huygens 150 years earlier, the nebula had changed form in the intervening decades. It is fascinating to ponder how ephemerality and transformation, so momentary on our world, in space play out on scales beyond a human lifetime. As Herschel said, much like the other members of its complex, the Orion Nebula is a young stellar nursery. Between 1 and 3 million years old and about 7 parsecs across, it forms part of the larger Orion molecular cloud complex. If you glance at the map, you will see that the Orion Nebula is marked fluorescent green. That indicates that it is a maser, a naturally forming microwave laser often produced by the jets from infant stars. The Orion Nebula has a mass equivalent to 2,000 suns, 1,500 of which comprise the Orion Nebula cluster, the stars which illumine the nebula proper, firing it in day-glow hydrogen pink. Keen observations have noted a hint of green in Orion's palette, a color that early astronomers could not explain. At first they concluded they had found a new element, just as Simon Newcomb had found helium, which they named nebulium. Today we know that the green color is due to a particularly tricky energy transition undergone by doubly ionized oxygen. To date, helium remains the only element first found in space. Orion's core is Theta 1 Orionis, now better known as the trapezium cluster, a group of 5, actually 15, stars crammed into roughly 10,000 AU, or the distance to the inner edge of our solar system's Oort cloud. The 5 components of the cluster readily visible to telescopes are labeled, from left to right, A, B, C, D, and E. The brightest of the group, and the only O-type, is C, a monstrous giant star 33 times the mass and 200,000 times the luminosity of the Sun. C is in fact a binary, with a B-type only a third as massive, orbiting it every 11 years. Together they emit a solar wind 100,000 times as strong as the Sun's. A dimmer second companion may be slowly escaping the group. A is a triplet star of 2 B-types and an A-type. The largest is 15 times the mass and 16,000 times the luminosity of the Sun. It is eclipsed by an as-yet unseen binary, possibly a T-Tauri star, and orbited by a further companion, at 90 AU. B is a quintet, an eclipsing binary, at between 10 and 100,000 years old, one of the youngest ever observed, orbited by 4 other stars. B1's companion is much smaller than B, and so likely far less evolved. Spectroscopy suggests that it is currently a G-type, like the Sun, but its 2-sun mass suggests that when it settles into the main sequence, it will probably be A-type. The other stars range in mass from 3 times the mass of the Sun to just 1/5 its mass, suggesting another young red dwarf. D is a bright B-type, 18 times the mass and 30,000 times the luminosity of the Sun, orbited by 2 fainter companions. E is a binary of 2 nearly identical protostars in a 10-day circular orbit, each about 3 times the mass of the Sun. Star formation means planet formation, and the Orion Nebula was one of the first regions in which protoplanetary disks were directly observed. Unfortunately, these infant solar systems are cursed at birth. The raging furnaces of the trapezium cluster are blasting their material away at a rate equivalent to the mass of Mars every year, enough to strip them bare in less than 1 million years. The stellar winds from the stars of the trapezium cluster and the wider Orion Nebula cluster sculpt the clouds of the nebula into wakes and ripples. In about 100,000 years, these winds will dispel the gas from the nebula entirely, and only the cluster will remain, gradually dispersing as it sails through the Milky Way. Just below the Orion Nebula is the Lins 1641 cloud, the westernmost extension of the Orion Nebula clouds. It is home to a loose string of forming stars, including her big Hara objects. It is one of 1,025 bright nebulae, and 1802 dark nebulae, compiled in the 1960s by astronomer Beverly Turner Linz, who, surprisingly, is still alive and working for the IAU. Finally leaving the star city of Orion, we make our way to NGC 2232, a sparse cluster of about 20 stars of higher metallicity than the Sun, suggesting, unsurprisingly, that they are young. The cluster centers on 10 Monocerotis, a binary star comprising a B-type star orbited by a smaller companion at a distance of 26,000 AU. And that, bar two recently discovered clusters about which I can learn little, takes us out of the Orion Aridus superbubble. I'm not entirely sure where to go from here. Maybe I'll follow the circle back home, or perhaps I'll just pick a direction at random. Say, the second star to the right. Whatever happens, I hope you will take the journey with me again. And of course, please like, comment, subscribe, etc. And stay curious, fellow seekers.